if you clicked on this video, you're either struggling with the basics of vector calculus or you feel like you're going to be interested in further expanding your own knowledge in math and challenging yourself on a course which you have not started on yet. So, if you saw the title, you know that today's topic would be finding the rate of change of a function with multiple variables. Now, we all know the rate of change of a function that has one variable, x, and another output variable, y. So we have, let's say, f of x is equal to x squared. Everyone knows that the rate of change of f of x in this case is going to be f prime of x or 2x, if you know the basics of derivatives. So, in this case, at 1, the rate of change would be 2. So f prime of 1 is equal to 2, which means that there will be a tangent with slope 2 at 1. So, how do we apply something like this in 3 dimensions, or maybe even 4 dimensions? Well, we have something known as the gradient operator. Now, this is basically like a pinnacle of vector calculus, and what it allows us to do is it takes a scalar field, x, y, z, and it outputs a vector field, which is in the format of partial derivative of f with respect to xi plus partial derivative of f with respect to y, j, plus partial derivative of f with respect to z, k. Now, this basically will map out a vector field which is in 3 dimensions in this case, which explains the rate of change of this 4-dimensional function. Now you might say there are 3 variables. How is it 4-dimensional? Remember, this f itself is an output variable. And these 3 are input variables. Now, this may seem too complicated, so let's keep the application in 3 dimensions. Now, let's say we have a function f of x, y is equal to sine or cosine x plus cosine y. In this case, to find the rate of change, we will take the gradient of f, in which we're going to do the partial derivative of f with respect to xi plus the partial derivative of f with respect to y, j. Now, the partial derivative of x treats cosine y as a constant. It treats y as a constant, so thus cosine y is also a constant, so this ends up being 0. And the derivative of cosine x is minus sine x. So we're going to have minus sine xi plus minus sine yj, because the same thing happens when we do the partial derivative of f with respect to y. X becomes a constant, cosine x becomes a constant, and cosine y becomes minus sine y. So we get this. Now, let's find the rate of change at 2 pi, 2 pi. In this case, we're going to have minus sine 2 pi, which is 0, plus minus sine 2 pi j, which is 0. So 0i plus 0j gives no rate of change in either direction, and it ends up being 0. So we have no rate of change in any direction. Now, if the vector field, this is a very obvious question, but if the vector field is two-dimensional and the scalar field is three-dimensional, how does it work out? Is there any way we can think of this the same way we think of derivatives as keys to finding tangents to any function at any given point? Yes. So, let's say we have a three-dimensional function that gives a hyperbola. Now, we will get a vector field. If we do the gradient operator on this given function, we will get a vector field that basically shows a bunch of arrows diverging from the origin. Now, when we wrap this plane around this, we're going to see this. And it perfectly explains the rate of change of this function. We take this point, let's say it's at 1, 0, and it's going to be here at 1, 0. Its displacement with respect to x didn't change, but all we did is we wrapped it around the hyperbola. So, the entire point of the gradient operator is to find the rate of change of any function, no matter any amount of variables, quickly and easily.